Good evening and welcome you all to the IPA50 webinar series, New Horizons in Physics. As many of you know, Indian Physics Association was established in 1970, and to commemorate 50 years of IPA, we are holding the webinar series in the current pandemic situation as we could not have the live conference. Today we have sixth lecture of this series, and the lecture will be given by Professor Sanjay Puri from Jawaharlal Nehru University, Delhi. Is going to be talking about the phase transitions, a topic which spans across the different fields of physics. And to introduce today's speaker, I would like to invite Dr. Prabhat Jaiswal, who started his research work in statistical and computational physics of soft matter under the guidance of Professor Puri. After his PhD at JNU, he went to Germany and Weizmann Institute in Israel for postdoc, and currently he is working as assistant professor in Department of Physics at IIT Jodhpur. I now invite Dr. Jaiswal to introduce today's speaker.
Thank you, Professor Nanal. Good evening, everyone. I'm thankful to the organizers, IPA, for giving me this wonderful opportunity to introduce our today's speaker, Professor Sanjay Puri. I really feel honored. Professor Puri obtained an MS in physics from IIT Delhi in 1982 and earned his PhD in physics from the University of Illinois at Urbana-Champaign in 1987. In the same year, he joined the School of Physical Science at JNU as an assistant professor. He has been at JNU since then and is currently a professor there. During this period, he has made several visits abroad and has been a visiting professor at Johannes Gutenberg University, Germany, at University of Manchester, UK, Cambridge University, UK, and Kyoto University, Japan. Professor Puri works in the areas of statistical physics and nonlinear dynamics. He has been particularly interested in the problems of pattern formation in non-equilibrium systems and has made many significant contributions to our understanding of the kinetics of phase transitions. So these include in particular the formulation of cell dynamical models to study the phase ordering dynamics, defect dynamics in disordered systems, and surface directed spinodal decomposition. I was actually fortunate to work on some of these problems during my PhD thesis. So Professor Puri has also made important contributions to the understanding of dynamical properties of granular materials, and he has published so far more than 200 papers and has written or edited 3 books. Professor Puri has also supervised, I think, around 18 students so far for PhD. And Professor Puri is the recipient of many prestigious awards like INSA Young Scientist Medal and Satyamurthy Award from IPA, B.M. Birla Science Award in the year 2001, Homi Bhabha Fellowship, Shanti Swarup Bhatnagar Prize in 2006, and the very recent one, Visitors Award for Research in Physical Sciences from the President of India. I just mentioned a few, the list is actually quite long. So he was given the Distinguished Alumni Award from IIT Delhi in 2013 and has been awarded also J.C. Bose National Fellowship by DST twice. Professor Puri has been an editor and associate editor of the Journal of Phase Transitions since 2000. He is also an elected fellow of the Indian Academy of Sciences as well as Indian National Science Academy. Furthermore, he has been also holding key positions in various scientific committees. So there have been many occasions where I felt deeply influenced and motivated by Professor Puri. One such occasion goes back to the year 2006 when Professor Puri was going to receive the Bhatnagar Prize. So many students actually from our department were going to the award ceremony. While leaving the department, we noticed that he was still working in his office, very, completely unaffected and working as usual. So that touched me a lot, and that actually inspired us a lot also. So now, without any further delay, I would request Professor Puri to deliver his lecture on the kinetics of phase transition. Professor Puri.
Let me just share my screen. Okay, I think it's, let me just make it widescreen. Yeah. I guess it's visible now, right? Huh?
Yes, we can see.
Yeah. Okay. Let me then start off. I'd like to start off by thanking Prabhat for this very kind introduction. I've been fortunate to have students like Prabhat who have sort of really enabled me to sort of pursue a wide range of problems in non-equilibrium physics. And frankly, your students become like part of your family. It's a second family to you, and you treasure your students as much as you treasure your children. So thank you, Prabhat. Second thing I must say is I'm really very grateful to Professor Vandana Nanal and other colleagues at Indian Physics Association. I think they're doing a wonderful job, the IPA, in terms of publicizing and popularizing physics in the country. And I really congratulate them on the job they're doing. And I'm very grateful to you for this invitation to speak on this occasion. It's really a very pleasant thing for me to do. Okay, I've been told that the audience consists of a spectrum of people, but would also perhaps include undergraduates and school children. So at the very outset, I should say that I will talk about the subject I will not sacrifice on the physics content, but I will sort of go very low on the mathematics content, okay? Because the I want to sort of illustrate the physics points, and the mathematics is something we can discuss. If you can email me and you can correspond with me and so on and so forth, okay? So I will not, I'll keep the physics content intact, but I'll try to say it in words rather than in mathematics. Okay, I have a long-standing interest in phase transitions. Phase transitions is something we are all familiar with from our childhood. Very quickly we realize that water exists in three phases. I mean, there's liquid water, which we drink. There's ice, which we get if we put water in the freezer. And there's water vapor, we get gas if we boil water, okay? Now, the fact that this same material exists in three different phases has fascinated physicists for many years. And as a matter of fact, as Vandana said at the beginning, phase transitions are ubiquitous across different areas of physics. For example, superconductors, a metal exists in the normal phase at high temperatures and in the superconducting phase at low temperatures, okay? So that's another example of but it's the same microscopically constructed material existing in two different phases, okay? So, so there's been a lot of interest over the last 200 years or so, and possibly the sort of initial, the starting point of that interest was triggered by van der Waals with his famous equation of state. And so the equilibrium aspects of phase transitions are something that people have studied for many years now, and many sort of landmark discoveries in physics and consequent Nobel Prizes are associated with contributions to the area of phase transitions, okay? Today I'm going to talk about a fascinating set of problems connected with the kinetics of phase transitions, okay? So clearly phase transitions take place in nature. Water can exist in the ice phase, it can exist in the water vapor phase, and it can exist in the liquid phase, okay? So the questions we ask when we talk of kinetic phase transitions is the following. Suppose I take a tray of ice out of the freezer and place it on the table, okay? It's now at room temperature. It would like to convert to water. What is the kinetic processes whereby this non-equilibrium ice state becomes water? Okay, so that's a typical question in the kinetics of phase transitions. Obviously, whenever you talk of kinetics, you have something that's changing in time, and it's a non-equilibrium problem. And as a matter of fact, in many cases, it's a non-linear problem also. Okay, so these are sort of the sort of terms you should keep in mind when you think of the kinetics of phase transitions. Okay, let me give you another example from your daily life. Okay, you have water vapor in clouds. By some process, the water vapor condenses into rain and precipitates on our head. So what is the kinetics whereby the water vapor or the gas phase converts to the liquid phase? Okay, so I will try to address some of these questions in my talk. They seem like very simple questions, but actually give rise to deep realizations in the area of phase transitions. In particular, the kinetics of phase transitions from ice to water have many similarities with the kinetics of phase transitions in the early universe, with the kinetics of phase transitions in superconductors, and so on and so forth. Okay, so by the end of this talk, I hope to have convinced you that the underlying universality in phase transitions, in equilibrium phase transitions, is also seen in non-equilibrium phase transitions. So that sort of would be the purpose of this talk today. Okay, and of course, I'm always available on email. If you write to me, I guarantee you'll get an answer in 1 or 2 days, definitely. So I'm always happy to sort of discuss this subject, especially with young students who might be listening to this talk. Okay, so here's a sort of broad overview of my talk. Don't worry if some of the terms are not familiar to you right now. I hope by the end of the talk, I will have explained everything in a fairly transparent manner. I'll start off in my customary sort of introduction. So that's the first set of statements. And then I will talk about the two prototypical problems of kinetic phase transitions. The first prototypical problem will be the dynamics of ordering of a magnet. Okay, again, as I said, don't worry if you don't understand precisely what that means right now. The terms will be explained as we go on. Okay, and the second prototypical problem one studies in kinetic phase transitions is the kinetics of phase separation, or the dynamics of phase separation of a binary mixture or a ternary mixture, or so on and so forth. This class of problems is very relevant to our engineering colleagues, and as a matter of fact, our sort of researches in this direction have been triggered by problems from the engineering community, as will become clear as I go on with my talk. Okay. I probably will not get to part D. I've just put it in there to sort of give you a flavor of the kinds of research problems we do with the concepts in B and C. And that's about the phase separation at surfaces, which Prabhat mentioned in his introduction. And then I'll end with the customary conclusion. Okay. So let's start off with my introduction. I already told you on the introductory slide that I'm going to consider the evolution of a system which has suddenly become thermodynamically unstable. Okay, and typically you make the system thermodynamically unstable by a rapid change of temperature or pressure. So for example, in the case of the ice taken out of the freezer, you put it on the table, means you suddenly heated it up to room temperature, and then you ask how the system starts to melt and how the phase transition becomes complete. Alternatively, for your water vapor in the cloud, the system is suddenly cooled down, and then you ask yourself the question, how does the water vapor condense, convert to rain, and fall on our heads? Okay, so I've already made these statements. As I said, these problems have been of great interest to many people, especially over the last 30 or 40 years, and they go under diverse names. Kinetics of phase transitions is the name I've been using so far. They also get called phase ordering problems, problems of domain growth, coarsening, and so on and so forth. Okay, and some 10 years ago, we reviewed the state of art in this area in this book by myself and Badhavan. It's an edited book, but this is a subject that's very dynamic and continues to change literally every year. Okay, As with phase transitions, kinetic phase transitions are ubiquitous. So problems in this area arise from very diverse fields, ranging from atmospheric physics. How does a cloud convert to water, to rain, to material science? How does a binary mixture of two polymers undergo phase separation? To metallurgy, how does a brass decompose into copper and zinc? And even as a matter of fact, to cosmology and astrophysics. This is not something I mentioned so far, but this is one of the most exciting areas in physics today, cosmology and astrophysics. And if you think of it, our current understanding of the universe is that you sort of started with a singularity, you had a big bang, the universe expanded. Initially, there were no particles, there was just a field of energy. The universe continued to expand. Various phase transitions took place. Elementary particles appeared, elementary particles formed atoms, and so on and so forth, and finally clustered into galaxies and stars and planets, etc. So as you can imagine, the universe was and continues to be a very sort of dynamical scenario, and many of the phases of the universe are described by phase transitions, or more precisely, kinetic phase transitions. Okay, so again, as I said, the purpose of this talk is to convince you that the ideas that apply to the melting of ice or the condensation of water also apply in the early universe. It's just that you have to change the entities or quantities that you are talking about when you go from water to the early universe, for example. Okay. I should emphasize that as physicists, we are usually interested in underlying universalities in systems, and this kind of universality is what I will try to emphasize in my talk out here today. Okay, so here's the first phase diagram. This is something we all encounter already in our higher secondary days. This is the phase diagram of water. And typically the experimentalist plots it in the temperature pressure plane. And we all know, we've seen this several times, that at low temperatures and high pressures, water exists in the solid phase. At high temperatures and low pressures, water exists in the gas phase. And at moderate temperatures and moderate pressures, water exists in the liquid phase. Okay, and the sort of physics principle that governs the particular phase you exist in at a given temperature and pressure is the minimization of Gibbs free energy. Okay, I say this because this is the principle that, I mean, an appropriate free energy is minimized in each and every phase diagram or phase transition that occurs in a physical system. Okay, so in this particular case, the Gibbs free energy is minimized. Okay, this phase diagram has several very interesting features. There are these lines of phase transition where first order phase transitions take place. At the first order phase transitions, there are discontinuities in the first derivatives of free energy, and that's what gives us latent heat, specific volume, and so on and so forth. And then there's this very fascinating point, which is the end of this liquid gas first order line, which is called this critical point. I emphasize the critical point because some of the most beautiful physics concepts of the last 50 years have been understood in terms of phenomena around the critical point. And I'm going to use a term out here, the renormalization group. The renormalization group framework has been sort of structured to, has been formulated to understand the physics around the critical point. Okay, so some of the most beautiful developments in statistical physics center around this critical point. In school, one also encounters this triple point, but probably from the point of view of a theoretical physicist, the triple point is not as interesting as the critical point. Okay, so this is the equilibrium aspect of the phase diagram. This is a phase diagram we've known for about 100 years, and I'm not going to sort of harp on it much more. Okay, I am interested in kinetics problems. So what is my kinetics problem? Ice being pulled out of the freezer. I start off with ice at 0 temperature in the freezer. So that's, let's say, on the pressure axis. I pull it out of the freezer and place it at room temperature on my table. Okay. At this new temperature, sorry, I have to go back to this. At this new temperature, ice likes to convert to water. The ice phase is unstable. What is the kinetics whereby I convert to water? Okay, so that's my first problem cast in the framework of this phase diagram. My second problem of supersaturated cloud. Okay, I have water vapor which is in the gas phase. Let's say I gently raise the pressure. The gas phase now likes to convert into the liquid phase because I'm on the liquid side of the phase diagram. Okay, the gas is unstable. What are the processes of nucleation and growth and so on and so forth, whereby the gas phase converts to liquid and then sort of precipitates on our head as rain. Okay, so that's my second typical problem in the context of this phase diagram. Again, I want to emphasize that the statements I'm making are universal across disciplines. The same sorts of things happen in material science. The same sorts of things happen in the early universe. It's just convenient to use the language of water when I talk about these phase diagrams. Okay. So as I said, I'm interested in kinetics problems. So let's investigate a little further these kinetics problems. And I'm going to sort of simplify the problem even further. I'm going to look at it in the context of a magnet. The magnet is equivalent to the fluid in terms of the phase diagram. Okay. So that's my next slide, and that's the dynamics of ordering discussion. So what I'm looking at here is what is a magnet physically? A magnet is a bunch of atomic spins, okay? And the atomic spins either like to point in the up direction, which is the north pole being up, the south pole being down, or they like to point in the down direction with the north pole being down and the south pole being up, okay? So a magnet is a bunch of atomic spins. What are the possible phases? The possible phases are that you can have a high entropy phase where everything is mixed up, all the spins are randomly oriented. That's the paramagnetic phase. And then you can have a low temperature phase where the spins are aligned parallel to each other, which is the ferromagnetic phase. Okay, so let's put this in the language of a phase diagram, exactly as I did for a fluid. So the experimentalist looks at a mole of atomic spins in the temperature magnetic field plane. For the moment, let me make my life simple. I just set the magnetic field H to 0 and focus on this axis, which is the temperature axis. Okay. Remember, the cardinal principle underlying my phase diagram is the minimization of free energy. That's always the case. The appropriate free energy in this case is the Gibbs free energy, which is internal energy minus T times the entropy. This is something that we've all seen several times in our undergrad courses. Okay, so at high temperatures, look at that factor E minus Ts. Okay, at high temperatures, because of the minus sign, you are better off lowering the free energy by raising the entropy. Okay, because you get a large minus Ts factor. If the entropy is large, that means the spins are randomly mixed and you have a paramagnetic phase. At low temperatures, you are better off reducing the free energy by lowering the internal energy. The best way of lowering the internal energy is to have the spins aligned with respect to each other, except it doesn't matter whether they're aligned up or they're aligned in the down direction. Okay, that doesn't matter. So at the low temperatures, below the critical temperature, you have the ferromagnetic phase, and in the ferromagnetic phase, all the spins point either in the up direction or in the down direction. The direction doesn't matter. As a matter of fact, physicists use this beautiful term, broken symmetry, to describe this phase transition. Okay, so okay, that's that's the equilibrium phase diagram. I told you I'm not interested in equilibrium problems. I'm interested in non-equilibrium problems. And I'm going to ask myself the following kinetic question. I start off at high temperature in the paramagnetic phase, rapidly quench or cool the system down to a low temperature, below the critical temperature. The system likes to now become a ferromagnet. What is the process whereby it becomes a ferromagnet? What is the sort of evolution of the system whereby the phase transition comes to completion? And that's the subject of my next transparency. So these are actually pictures obtained from some kind of Monte Carlo simulation, but you can see them in many textbooks on this problem. I have a process happening in time. So I label these snapshots by the time. As you can see, the time increases. I start off with time t equal to 10, then 50, 200, etc., etc. At time t equal to 0 is when I do my temperature quench. So at time t equal to 0, I have a paramagnetic phase. So that's somewhere up here. I haven't shown it out here. That's a random mix of up spins, which I denote by black, and down spins, which I denote by white. And as time goes on, the system starts to undergo the phase transition, the kinetic phase transition. Spins coagulate, and there are regions of black or up spins, and there are regions of white or down spins. Okay, so these domains form in up spins and domains in down spins. Remember, the system is equally happy being all up or all down. So as time goes on, the domains of up spins grow and the domains of down spins grow, and they grow and they grow. And finally, at time t equal to infinity, which is somewhere at the bottom out here, the system converts into a system with all up spins or all down spins. So about half the time, if you do this experiment 1,000 times, about half the times you'll get all up spins, and half the time you'll get all down spins. And at t equal to infinity, the phase separation, the phase transition is complete. That's the sort of picture you should have in your mind. Okay. So now you understand what I mean by broken symmetry. At the t equal to infinity state, the system has become ferromagnetic, and it's broken the up-down symmetry it started with. It's now by pointing all in the up direction or in the down direction. Okay. Okay, now let me sort of emphasize a few points out here. The first is as a theoretical physicist, I like to write down equations which describe this evolution. And I've already told you this is a strongly non-equilibrium process. The system is changing dramatically with time. So the equations that describe this are typically non-linear partial differential equations, which are analytically not solvable. Okay, so that's the first thing you must keep in mind, that I cannot analytically solve for this evolution process except in a few very special cases. Okay, but nevertheless, as a theoretical physicist, I would like to have some understanding on the evolution of the system, and my evolution my understanding is obtained in terms of the following paradigm. I realize that in the bulk of these domains, the system is in equilibrium. Here it's come to equilibrium in the up phase. Here it's come to equilibrium in the down phase. All the action, so to say, is happening at the interfaces. The interfaces or the kinks or the domain boundaries, they go under various names. That's what is moving around basically. And those are what kinks and anti-kinks are annihilating with each other. And the system is forming larger and larger domains as time progresses. Okay, so I'm going to use these sort of defects of the system. I use that defect, by the way, in physics is a good term. Okay, so these defects or these domain boundaries are what will be used to describe the evolution of the system. So that's this. I've got a set of statements out here. Let me just go through it. So the first statement I just made, that the domain growth is driven by the drive of the system to get rid of these domain boundaries or defects. I can actually write down an equation for the evolution of the defects. Remember, I promised you no mathematics. So let me just sort of intuitively argue this equation. This equation is basically the following statement, that at any point on the interface, the velocity is proportional to the local curvature. So it's just the intuitive statement that the more curves the system, the faster that interface or defect moves basically, okay? So this is something that's well known in the literature as the Allen-Kahn equation. And if you just do dimensional analysis on this Allen-Kahn equation, you get your first important physics result. And that is that you find that the length scale of these domains, as you can see, the length scale is growing. It grows in time as the square root of t, okay? So that's the sort of first important physics result. These domains coarsen with time and they grow as the square root of time, okay? The next important physics statement, again, I'm going to just, I put it in a sort of mathematical language, but I'm just going to argue it intuitively for you, is the statement that the system shows what's called dynamical scaling. And dynamical scaling is simply the statement that the picture at 500 or the pattern at 500 or the morphology at 500 is analogous to the morphology at 10, okay? All that's happened is that the scale of the morphology has increased or the length scale of the domains has increased with time. That's the sort of picture you have in your mind. And you can use this sort of interface analogy to understand how these domains are moving around. That gives you the length scale. And you can understand the morphology in terms of something that's called the correlation function or the structure factor. And that's typically what you see when you shine a beam of neutrons or light or whatever your favorite probe is of this system basically, okay? So that's our first example of kinetic phase transitions. This is the dynamics of ordering of a ferromagnet. I want you to take the following thing away from this transparency, that I cannot get a complete analytical handle on this process. So I use these defects or domain boundaries or kinks or whatever you want to call them to encapsulate the dynamics, non-equilibrium dynamics of the system, okay? I emphasize this because I'm going to come again to this point on my next set of problems, okay? So here's my next set of problems. And again, I'm going to do this only at a pictorial level. My next set of problems concerns the ordering of a superconductor or a superfluid from the normal state. Again, I think superconductivity is something that you are all familiar with. Superconductivity is simply the following phenomenon that for given a certain metal, at high temperatures, it's in the normal phase. And at low temperatures, it's in the superconducting phase, where miraculously almost the current flows without any resistance whatsoever, okay? Similarly, fluids at high temperature, they are in the normal phase. At low temperatures, they come into the superfluid phase. And in the superfluid phase, the fluids flow without any viscosity. So if you set up a circulation in a cylinder of a superfluid, it's just going to keep rotating all the way up to infinity, as a matter of fact. There's nothing to sort of dissipate the motion of the superfluid, okay? So this is also an example of a phase transition. The equilibrium aspects of it are well understood. There are many famous names associated with this, including that of Bardeen, Cooper, and Schiffer, who gave the famous BCS theory of superconductivity. I am interested in the kinetics of this phase transition. So I'm going to ask myself the following question. If you quench your system from the normal phase down in temperature into the superconducting phase, how does the phase transition proceed? Okay, and that's going to be the subject, that non-equilibrium process is going to be the subject of my next transparency. Okay, so that's again, this transparency requires some explanation, but there's no problem. We have all the time in the world, and let's try to understand what this evolution is saying. Okay, so I should say the following, that you know, when you're talking of superconductivity or superfluidity, this is a quantum mechanical phenomenon. Okay, there's nothing classical about this phenomenon. It's a purely quantum mechanical phenomenon. And whenever you have a quantum mechanical phenomenon, you have to describe it in terms of a wave function. And the wave function has an amplitude. So that's point one here. The wave function has an amplitude, which is not very important for us. And it has a phase angle. Okay. In the BCS theory, or in the Bardeen-Cooper-Schiffer theory, the difference between the normal phase and the superconducting phase is the following, that this phase angle is random in the normal phase. Okay. And in the superconducting phase, the phase angle is uniform everywhere. So the system has a macroscopic phase, or the same wave function describes the entire system. The same is true for a superfluid. Okay. Okay. So with that background, I can now tell you what sort of we are seeing in this picture. What we are seeing in the picture is the following. You are seeing the evolution of this phase angle theta out here at different points in space. I start off at time equal to 0, somewhere up here, where the phase is incoherent. Theta is different at all points in space. And then I rapidly quench the system down. It likes to now go into a superconducting phase. How does it progress from this incoherent theta to a coherent value of theta everywhere in the system? Well, that's the non-equilibrium evolution I've shown here. I just want to sort of point out the following, that these different colors in my snapshots, let's look at the last snapshot at the latest time. These different colors denote three small windows of the phase angle. So this black is some small window, the red is some other small window, and the green is some third small window. Okay. Yeah, don't get scared by all this. In 2 minutes, it will become clear. I draw your attention to these points where these three colors meet. Okay. Think about it in the following way. If you go around this point where the three colors meet, that is what's called a vortex defect or an anti-vortex defect. Okay. If you go around this point, the phase angle changes by 2 pi. Okay. And the vortex is a very standard sort of paradigm of pattern formation. The simplest way to create a vortex at home is to fill up your sink with water and then unplug it. Let the water drain out, and towards the end, it will create this vortex type of structure as it sort of drains out of the bottom of the sink. Okay, so this vortex picture is something that you see in the galaxies, you see in the early universe, you see in your water draining away, and you also see in this phase transition of a superconductor. Okay, so essentially what's happening here is the following, that earlier my defects were interfaces, right? They were the domain walls between up and down phases. Now the defects are the vortices and the anti-vortices. These vortices and anti-vortices move around, they coalesce with each other, form larger and larger domains, where you have larger and larger regions of the angle being parallel to each other. And finally, at time t equal to infinity, the phase transition is complete. The angle everywhere has become uniform, except it can live anywhere on a 0 to 2 pi. It can live anywhere on the dial of a clock. Earlier, remember, when my symmetry was broken, all the spins became either up or down. Now, when the symmetry is broken, all the spins point in a particular direction. Okay, so that's my second statement out here. Again, the paradigm is that this is a non-equilibrium system. It's a non-linear system. I cannot understand it analytically, but I can use these defects to get a handle on the kinetics. And this is something that we actually did a long time ago with my collaborator, Alan Bray. We found that again, the growth law goes as the square root of time. So the growth law in this case is the size of the vortices. Earlier it was the size of the interfaces. Now it's the size of the vortices. And again, we found this dynamical scaling property, which is the statement that this pattern is similar to this pattern, except the scale of the defect has increased with time. And that increase goes as the square root of time, basically. Okay. Okay. I just want to sort of take 2 minutes and sort of discuss this in a different context. Remember, one of my important sort of themes was to emphasize to you how universal this whole process is. About 10 years ago, we heard a lot about the Higgs boson. If you remember, all the newspapers were full of the Higgs boson. The Higgs boson was being looked for at CERN. And if you remember sort of reading the articles that came at that time, the Higgs boson has a very important role in electroweak theory in that it gives mass to its partner particles by a process of symmetry breaking. Okay. What I want to emphasize is that that is precisely a phase transition as is the superconducting phase transition. It's actually the same phase transition, just in a different language. Okay. So the dynamics whereby the Higgs boson gives mass to its partner particles is exactly the dynamics whereby a superconductor undergoes ordering from the normal phase into the superconducting phase. Okay. So it's a totally different problem. Here I'm talking of condensed matter physics. There I'm talking of particle physics. But the phase transitions are the same, and the kinetics of the phase transition is the same. Again, I can reinterpret my language. One is very interested in liquid crystals. All your computers have liquid crystal displays. Liquid crystals are rod-shaped molecules. They've been very important in the Indian context because important research has been done in India on liquid crystals. And these rod-shaped molecules can point either in all parallel direction, which is called the nematic phase, or they can be randomly oriented, which is called the isotropic phase. Okay. Again, it's the same phase transition as the one I'm showing you out here. And the kinetics of ordering from the from the isotropic to the nematic phase is the same as the kinetics of ordering from the normal to the superconducting phase. Though again, one is talking of different entities and so on and so forth. The underlying paradigm for all these phase transitions, both in equilibrium and in non-equilibrium, is that these vortices or monopoles or whatever drive the phase transitions in this system. Okay, so far I've been talking about the dynamics of ordering. Okay, I want to spend the last 10 minutes talking about, so this is the first set of prototypical problems of the kinetics of phase transitions. The second set of prototypical problems are of more interest to the engineering community, and these problems actually originate from the engineering community. So this is part C of my talk. This is the dynamics of phase separation. Okay. Of course, the engineering community looks at these problems, but we also encounter them as physicists. Typically, one encounters, let's say, an oil and water mixture or a polymer mixture or a binary alloy, which is a mixture of copper and zinc if it's brass and so on and so forth. Okay. Energetically, the two components like to phase separate. Entropically, they like to mix up because that gives you more entropy, right? Remember, it's always a trade-off in minimizing the free energy, which is E minus Ts. You can either lower E, which is coming with a plus sign, that is go for the phase separated state, or you can raise the entropy, which is coming with a minus sign, and thereby lower the free energy. Okay, so at high temperatures, you are better off increasing the entropy or in the homogeneous phase, and at low temperatures, you are better off going into the phase separated state where oil and water sit separately. Okay, again, this is a phase transition which has been around for 100 plus years, 200 years maybe, and people have worried a lot about the phase separation, phase transition. We now have a pretty good understanding of the equilibrium aspects of this phase transition. I now am interested in the kinetics of this phase transition, and this is the problem that's been of interest for the last 30, 40 years. I start off at time t equal to 0 in the homogeneous phase, which is at high temperature. I rapidly quench the system down. I cool the system down below what the engineers call the miscibility gap. And I ask how the system undergoes phase separation, how it goes to its new equilibrium phase. Okay, so that's the process I'm going to do. I'm going to rapidly quench it from the homogeneous region to the phase separated region, and that's going to be the subject of my next transparency. Okay, so here's the phase separation of a 50% mixture of oil and a 50% mixture of water. Okay, if I just go back to my phase diagram, I emphasize that the variables I use are the fraction of oil is on the x-axis. So the fraction of oil goes from 0, which means no oil, to 1, which means all oil. Correspondingly, the fraction of water goes from 1, if there's no oil, there's only water, to 0, if there's only oil, there's no water, basically. Okay, so that's the x-axis, and the y-axis is the temperature. So right now, I'm doing a quench down this middle line where there's 50% oil and 50% water. That's the picture I'm showing you in the next transparency. Okay, so here's an evolution of an oil and water mixture in 50-50 proportion. At time t equal to 0, when I start my experiment, I am in a homogeneous phase. Oil is black, water is white, and in my t equal to 0 snapshot, which I haven't shown here, oil and water are homogeneously mixed. Now, because I have quenched to low temperature, they like to phase separate. I develop domains which are rich in oil, which are the black regions, and I develop domains which are rich in water, which are the white region, and they're just a beautiful bicontinuous kind of structure because of my 50-50 mix of the system. As time goes on, my domains grow, the oil-rich domains grow, the water-rich domains grow, and they grow, and they grow, and finally at time t equal to infinity, somewhere out here, the phase transition is complete. But in my final state, I have a large blob of oil and a large blob of water separated out. Okay, this is fundamentally different from the ordering of the ferromagnet I talked about earlier. In the ordering of the ferromagnet, there was no conservation law. Up spins could convert to down spins. Here, I don't have that liberty. At each time in the evolution, I have to maintain the 50-50 composition of the mixture, and also in the final state, I have to maintain the 50-50 composition. Okay, so in this case, actually, the process is much more tortuous. What happens in this case is that this droplet of water, of oil, this small droplet of oil evaporates, transports through the underlying water, and goes and deposits on a larger droplet of oil somewhere else. So the evolution is essentially the following, that small droplets get eaten up by larger droplets, which get eaten up by yet larger droplets, and finally at the end of the day, you only have one large droplet of oil and one large droplet of water left. This is a much more difficult process to analytically understand. Again, the paradigm is the same. The phase separation is driven by defects, but I have an important conservation law, and that conservation law tells me that at all times in my evolution, I must have 50% oil and 50% water. And that means that if an interface wiggles somewhere, all other interfaces must readjust so as to preserve the composition of the mixture. Okay, so this is a problem that is not fully understood in spite of 50 years of research on this problem. This problem is not yet fully understood in the sense that we are still not, we know the growth law. The growth law is simply T raised to power 1/3 as opposed to T raised to power 1/2 in the non-conserved problem. But we don't know the scaling form of the structure factor. Okay. Remember, in the phase separation problem, you have the option of an asymmetric quench also. For example, I can fix any composition I want. So let me consider a quench down this line where I have 30% oil and 70% water. Okay, so that's a quench along. So that's the 30% oil, 70% water. So that's a quench from that high temperature here down here. Okay, what does the corresponding evolution look like is my next transparency. Again, I'm looking at an oil and water mixture, but there's 30% oil, which is black, and 70% water, which is white. At time t equal to 0, I start off with a homogeneous mix of oil and water. That's my high temperature state. I rapidly quench the system. It starts to phase separate, but because oil is now in a minority phase, I get droplets of the oil in a majority phase of water, which is the sort of large white picture out here. The droplets grow with time. This process is known as Ostwald ripening in metallurgy. These droplets grow with time and grow and continue to grow as a matter of fact until finally your phase transition is complete and you have one large droplet of 30% oil and correspondingly 70% water. Again, the physics that drives this phase separation is the same evaporation condensation process. The smaller droplets have higher chemical potential. They evaporate, transport through water-rich regions, and go deposit on larger droplets elsewhere. The larger droplets then evaporate in turn and go deposit on yet larger droplets elsewhere, and so on and so forth. Okay. I just again want to make a point out here. Maybe the point is to prove that statistical physicists are sort of willing to go anywhere their fancy takes them. If you think about it a little bit, these kind of processes also occur in sociological or economics contexts. Okay, and as a matter of fact, statistical physicists now make contributions to both sociophysics and econophysics. So for example, in econophysics, you could think of this as a process where smaller companies are being eaten up by larger companies, and the larger companies are being eaten up by yet larger companies. And then at the end of the day, probably you have only Jio surviving as your mobile network provider or some such thing. Okay, so you can sort of have that sort of imagination in your mind. This is not just, I mean, people have actually used these kind of models to study problems in both sociology and economics. I don't want to go into details of that here. I'm not an expert on that. My problems are usually taken from material science and engineering situations. And that's but these things also apply in that context. Okay, I think I was told about 45 minutes. So I think that sort of, again, I'm not going to put this mathematics details on you. I'm happy to give you references if you're interested. I'm happy to sort of answer emails if you write to me. Some of our recent research, let me just say 2 lines about this. Some of our recent research has focused on the problem of phase separation at surfaces. And as a matter of fact, Prabhat Jaiswal, who introduced me earlier, has actually worked on these problems. So here the problem you're interested in is the following. You have a surface in contact with a binary mixture. The binary mixture is unstable to phase separation. So it phase separates into oil and water mixtures. At the same time, the surface is preferentially wetted by oil. Okay. What is the interplay of the kinetics of wetting and phase separation? Okay. And again, I'm not sort of going to go into details of this process because this is not the appropriate sort of occasion for it. But as you can imagine, problems like this are very interesting in the context of nanolithography. In nanolithography, you have a surface with a pattern on it, and you ask yourself the question, how do you replicate that pattern into the bulk? Okay. So questions like phase separation in contact with the wetting surface is interesting again in various engineering situations in the context of micro etching and so on and so forth. And these are problems that me and my collaborators have been looking at. I'm happy to say that in this context, I have lots of collaborations with people in chemical engineering departments, people in metallurgy departments, and we've had a very fruitful sort of exchange of ideas. A physicist looks at things from a more universal perspective. He or she tries to identify underlying universality in all problems. Whereas our engineering colleagues have more specific interest in applications and specific systems, and it's a sort of good combination of skills and talents, and it's been very enjoyable interacting with various engineering colleagues. Okay. So I think that sort of brings me to the end of my talk. I won't talk about phase separation at surfaces. Quickly flash a picture at you of my recent paper by Prasenjit Das, Jaiswal and myself. This is phase separation on a physically patterned surface. So the surface has some teeth on it. And again, the question you ask is, how do you replicate this surface structure in the bulk? Alternatively, you can have a chemically patterned surface where the surface has patches which prefer oil and water. And again, the question you ask is, how do you sort of replicate this checkerboard structure into the bulk? These are both questions that Das, Jaiswal and myself have had interest in and just sort of published on this year. Okay. I think let me then sort of come to my conclusion, and then I'll try to answer whatever questions there are. We focused on the kinetics of phase transitions, and I hope I convinced you that the kinetics of phase transitions, like the statics of phase transitions, is universal, okay? i.e., the same concepts apply in the melting of ice, the condensation of water, in the evolution of the early universe, in superconductors, and so on and so forth. Okay, it's the only difference between these different systems is the difference in time scales and length scales on which things happen. Obviously, the early universe length scales will be very different from what is happening in superfluid helium. Okay, but the kinetics of phase transitions is universal, and the two standard problems are, by now I hope these terms are clear. The first standard problem is the dynamics of ordering of a ferromagnet, and the second standard problem is the dynamics of phase separation of a binary mixture. And though I use the language ferromagnet and binary mixture, these processes apply in a vast variety of different physics situations. Okay. My second important observation is that these problems are non-linear, non-equilibrium problems. They're analytically tough to solve, okay? Nevertheless, as a theoretical physicist, I want to make some progress on these problems. And the progress has come in terms of using the defects in the system to capture or encapsulate the kinetics, okay? So the defects in the ferromagnet, the defects for interfaces. In the superfluid state, the defects for vortices. In the early universe, the defects are monopoles and so on and so forth. So you can think of these defects as elementary particles, and I can capture the pattern kinetics in terms of the motion of these elementary particles and their interaction and annihilation and so on and so forth. Okay. I very briefly mentioned, just to sort of give you a preview on the kinetic interplay of phase separation and wetting. I'll be happy to sort of discuss that further with anybody who's interested. Okay, I think this is a good place for me to stop. Thank you so much.
Thank you, Professor Puri, for such an exciting and very insightful talk on the kinetics of phase transition. I think you broadly covered so many topics, and it gives us the universal picture of this, application as well as fundamental science both. And I think we already received a couple of questions on YouTube, and response is good.
Yeah.
And we also maybe but first we can pick up the questions on the Zoom platform. So those who are interested in asking the question, please unmute yourself and please ask the question.
Should I remove this full screen or should I leave it on full screen? Huh?
I think you can stay just in case some question needs going back.
Going back to one of the slides. Okay. Okay.
Any questions on the Zoom platform? Maybe meanwhile, I can read a couple of questions from YouTube. So we got these very fundamental and exciting questions. So the question is by Professor Basuraj Agali, and the question is as follows. So he's asking, you mentioned about the renovation group earlier.
Right. Yeah.
What is it and how can it help in understanding the phase transition?
Okay, that's a very sort of important question. Let me just go back to my sort of first transparency where I showed the phase transition of water, of liquid. Well, this is the same phase diagram. This is the phase diagram of water, say, okay? And the key point I want to sort of emphasize is that something very curious happens at this critical point. What happens at this critical point is that the correlation length of the system becomes infinity. It actually becomes infinity, okay? So what that is saying is the following, that at the critical point, the fluid is highly correlated. In physical terms, if I give a poke to the fluid at one point, the entire system will respond back, okay? So a slight stimulus somewhere will lead to a large response of the system, basically, okay? And this is possible because the correlation length becomes infinity. This happens in many situations, and all critical phenomena are sort of characterized by these correlation lengths becoming infinite, okay? Renormalization group is something that exploits the divergent correlation length. It exploits the correlation length becoming infinity to make a set of tools to solve for critical phenomena in the vicinity of the critical point. The tools are somewhat technical, but basically you make use of this fact that the physical length scales are becoming infinite to solve the problem. And the tools to do this were developed by well-known names like Leo Kadanoff, Michael Fisher, and Ken Wilson. Ken Wilson actually won the Nobel Prize for this work, I think in 1983 or 1982 or something, basically. Okay. But if you want to sort of email me, I'm happy to answer, send you some references where you can actually read about the renormalization group. It's one of the most fundamental tools in modern statistical physics right now.
Hello, can I ask a question?
Yeah.
Hello? Hello? Hello?
Yes, please go ahead.
Can you hear me? Hello?
Yes, we can hear you.
Okay, fine. Yeah, I'm Ajit Srivastava, Professor Puri. Thank you.
Ajit, you are not very audible. Can you be a little louder?
Can you hear me better now?
Yeah, clear. Thank you.
Okay, thank you. Professor Puri, you mentioned in the beginning that you discussed the growth of domains by motion
Yeah.
of boundaries or defects. Now, I'm actually concerned about the shape of the domain. For a first order transition, we know the shape of initial domains are spheres or depending on curvature term. For second order case, what determines the initial shape of the domains? We know the size in terms of correlation length, but
Yeah.
the actual shape of the initial domain.
See, Ajit, I mean, that's a very good question. But I mean, the scenarios described here, you are actually interested in the length scales of the system diverging to infinity. So the correlation lengths, the domain lengths are going to infinity, and the shape of the domain is not consequential at infinity, because the shape of the domain is on a certain scale and the length of this domain itself is going to infinity, basically.
Yeah, but
Okay.
the initial, the
Yeah,
domain
the
is growing
initial
eventually.
density of defects, etc. I mean, that would very much depend on the underlying symmetries of the system, for example. Okay. But I think typically the simplest nucleus that forms in a cloud, for example, you would consider it to be a circular nucleus. But if you have a crystalline, underlying crystalline structure, then you would have facets and so on and so forth in your nucleus. I don't know whether that answers your question. Yeah.
Yeah, I mean, it's in
But
that direction, but let me just pursue a little bit.
yeah, this density. Yeah, this density of defects and the size or shape of the defects is dealt with in what's usually called the Kibble-Zurek sort of scenario. Here we are asking the question, what happens asymptotically in time? And asymptotically, you lose the initial memory of the shape of the domains, basically.
But just from the kinetics of phase transition, do we have this much information to determine actual shape of initial domains, or we don't have that information? I mean, the density of defects only determines the size of the correlation domain, not the shape, actual shape.
Yeah. No, these okay. So as I said, these scenarios do not worry about the size of the domain, the shape of the domain.
Shape of, okay.
But if you sort of write down microscopic free energies, and you try to sort of get some ab initio inputs into those microscopic free energies, then you can have some understanding of the shape of the initial nucleus and all that, which sort of starts this domain growth process.
Okay.
Yeah. But then again, and that's what I was trying to emphasize, that becomes one of the non-universal features. I mean,
yeah, sure. I agree with that.
Whether whether it's a crystal phase separating or whether it's liquid or so on and so forth. Right.
Yeah. I have one more question. Can I ask right now? Should I wait because other people?
Yes, please. Of course.
Okay.
You're
so
an
this
friend,
question is about your oil. Okay. Yeah, probably. It is oil-water example for conserved order parameter. You showed the case for them 50-50 case, they were large regions, whereas for a 30-70 case, they were only droplets of oil. Is percolation important in this case?
Yes, it's actually very important. I'm glad you asked that question. The bicontinuous structure percolates, as you can see from this snapshot. Right? But on the other hand, in the droplet scenario, only the water phase percolates. So in 2D, as soon as you go away from 50-50, you stop percolating in 2D. In 3D, I think there's some window in which you can have percolation, basically. Okay, but in 2D, as soon as you go off critical, you cease to percolate, basically.
Thank you very much. Okay.
Sanjay, we have another question from YouTube viewers. Is the entropy decreasing in phase separation? How does it happen dynamically?
I would say the entropy is decreasing overall, because remember what the equilibrium is. The equilibrium is dictated by the minimization of E minus Ts, right? Now you've lowered T and gone into a state which would like to be ordered, basically. So the entropy decreases with time and the free energy also decreases with time. You start off at a high temperature, the entropy is high to minimize the free energy. Then you quench the temperature. Now the energy, the entropy becomes low, again to minimize the free energy at that lower temperature. Sorry, did I answer that question?
Yes, I think.
Okay, the one-line answer is the entropy decreases as you go from the disordered phase to the ordered phase. It's as simple as that, yeah.
Okay.
The initial phase is disordered, paramagnetic. The final phase is ferromagnetic, so you reduce the entropy.
Okay. Shall I read another question from YouTube?
Yes, please.
Okay. Why phase transition to superconducting phase is limited to only some materials and not possible for all materials in general? And there is a compliment also. It's a very fine talk indeed.
Sorry?
So there was a compliment with the question also.
Oh, okay. I thought that was the second question. See, I think the point is, okay, now this is a very sort of fundamental question. And see, in the first theory of superconductivity, which is the BCS theory, or the Bardeen-Cooper-Schrieffer theory, there you really don't, you need these Cooper pairs. The Cooper pairs need to form a Bose-Einstein condensate and so on and so forth. Okay, it's a very beautiful and remarkable theory. Anyway, the point is the following, that the temperature there has to be below the temperature of Cooper pair formation. It's as simple as that. Okay, and not all systems will not allow you to form Cooper pairs, for example. Okay, so I mean, wood you will not expect to go superconducting, but metals, many metals form superconductivity, except the temperature may be very different. It may be 3 degrees Kelvin in some case, it may be 5 degrees Kelvin in some case, and so on and so forth. Okay, but the formation of Cooper pairs is a must for superconductivity of the old kind. Now, in the new set of superconductors, that also goes out of the window. Theoretically, those are still not understood. And as one knows, one can have superconducting temperatures of 90 degrees Kelvin, 100 degrees Kelvin, and so on and so forth. Okay? So, but these are again a specific set of materials, which are these rare earth doped compounds. Yeah. But again, in this case, the BCS theory is not applicable as far as one knows. And there is no good theory for the new family of superconductors, which were discovered 1987 onwards. In the old family, only metals showed superconductivity. Okay.
Okay, thank you. So this question is related to the vortices in the superfluid state. So the question is, what is the physical state of such vortices? Whether these vortices are in normal state or still in the superfluid state?
Okay, yeah, let me go back to that snapshot. See, the vortices are defects, and the global aim of the system is to remove defects as far as possible. Okay. So I would say that as long as there are defects, it is still in the normal phase. Finally, when all the defects have been annealed away, zero defect state, then I am in the superconducting state. So as long as the defects exist, it is not in the superconducting state. That's the answer to that question. The phase transition is complete when this phase angle theta becomes uniform everywhere. That's the way to look at it. Okay, and for it to become uniform everywhere, that means there must be no circulation of the phase as you go around any point, etc. I.e., there should be no vortices or anti-vortices left in the system, basically. Okay.
Okay. Okay. So another question from Uttam Pal from YouTube. At the vicinity of the first order, I think it's a comment. At the vicinity of the first order transition, correlation prevails. indicating the phase to a quantum phase. Is it not?
I didn't get the question. Sorry, what is the question?
So it's at the vicinity of the first order phase transition. Correlation actually,
okay, so that's
just previous. Yeah. So that indicates the phase
one of these
to
lines
a quantum
basically.
phase.
Somewhere near these. Yeah.
So that indicates the phase to a
No,
quantum
what is the
phase.
question? I didn't get it.
It's a cross question actually. Does this indicate the phase transition to a quantum phase in the vicinity of the first order phase?
No.
Yeah.
No. See, there are quantum phase transitions and there are classical phase transitions. Okay, this is understood as a classical phase transition. This particular example of the fluid. Okay, but yeah, let's not mix up classical and quantum phase transitions. There's a whole different branch of quantum phase transitions which show quantum systems which show similar phase transitions. The superconductor, for example, you could say is a quantum phase transition. But these are thermally driven phase transitions, and it's not sort of very, at the temperatures you are interested in here, quantum effects are really not very sort of germane, basically. Okay. Yeah.
Professor Puri, can I also ask one question?
Of course, please.
So this regarding this Allen-Kahn equation. So in the context of superfluid now, so there was, let's say in the Allen-Kahn equation, we see one velocity term here in terms of the Allen-Kahn equation. So there would be then many such velocities, or am I like for the superfluid,
Yeah, so see the boundary of the interface out here, that's this A vector in the Allen-Kahn equation. So you write down the velocity everywhere on the boundary. That boundary is equivalent to the core of the defect out here, this one. So you would write down the velocity of every core of all the defects. And then think of, forget about the rest of the system and try to write down the interaction equations for these cores of the velocities, basically, for the velocities of the cores. That's how you would sort of try to capture this process. I mean, again, as I said, one is using these defects to sort of capture the phase transition, kinetic phase transition process. And the velocity of the core of the defect is what's important, basically. Okay. So you would write down velocities for all these cores and then see how they interact with each other, basically.
So any more questions from the Zoom platform?
Can I ask a related question to Prabhat's question?
Please.
Yeah. About this Allen-Kahn equation, actually. This is for a dissipation dominated dynamics. So
that's for a dissipation dominated.
So for example, for early universe case, it will be very different equation, which will have the inertia term also.
You'll have an inertial term in the early universe equation. Yeah. Okay. And people have written down the counterpart of these equations for early universe scenario also. Yes. Again, you have a dissipative term and you have an inertial term. So there's a crossover from an inertial regime to a dissipation driven regime in those models. Yeah.
Yes. Actually, the question which was asked.
I mean, you could also include the inertial. Yeah, Ajit, you could also include initial terms in this process, but they are usually negligible because the friction, the dissipation is much larger. Much larger.
Sure, I understand. I just wanted to ask one more question about when somebody was asking question about the core of the vortex. And normally we are told that this core of the vortex is in normal phase. Outside it is the superfluid phase. But what we know is that this the order parameter actually vanishes only at a single point.
It's
non-zero away from a single point.
Right.
But literally, it vanishes only at a point. So is it reasonable to call that core is the normal phase? And
I think. Well, I would say that. See, if you, I mean, you don't have a coherent. If you look at this core, you don't have a coherent phase in the region of the core. If you go further away from the core, you have a coherent phase. So I would say that in the Ginzburg-Landau theory, where you have a coherent phase is the superconducting region, and where you don't have a coherent phase is the non-superconducting region. Certainly the core is one place where you don't have a coherent phase.
Absolutely.
But even in the
Got it.
vicinity of the core, you don't have a coherent phase, right?
Okay.
You should have some region of macroscopic coherence to have superconductivity in the, so you can say that far away from this core, most of the sort of angles are sort of more or less uniform, basically.
Right.
Naturally, at the core, at the singularity, is where the angles really start to go crazy, basically.
Right.
Again, you could ask the same question, Ajit, in the context of this ferromagnet, okay? You could say that at the defect, it's not ferromagnetic because the magnetization is zero at the defect. But as soon as you go a little away from the defect, then you come into the bulk of one of the domains or the other domain, basically.
Right.
So you could say those regions are magnetized, basically. Right?
Yeah, sure. Okay. Yes, thank you. Yeah, sure.
Okay.
So there is another question related to the subsequent question to the quantum phase transition. So in the liquid vapor phase transition, people have observed the quantum phase transition. What is your comment?
I mean, how does it mean observed quantum phase transition? I mean, quantum phase transition is a very sort of well-used term, but I mean, they have observed quantum effects. Is that the statement in the liquid gas transition? Or quantum corrections? What does it mean exactly?
It's not quite clear even. So I could not.
Have they observed quantum corrections? These are the questions you could ask. I mean, certainly everything is quantum mechanical, so one would not be sort of surprised if one sees quantum effects. But usually when people talk about quantum phase transitions, it has a different meaning. There you don't have see, in this case, the phase transitions are thermally driven. You change the temperature and the entropy changes. In the quantum phase transition, you sort of, the temperature is zero and you go across some quantum critical point, basically. Okay. Typically, the temperature is zero. As soon as you turn on a little temperature, all the quantum effects get washed out in quantum phase transitions, basically. So I would not be surprised if there were quantum effects out here, but the primary physics is not quantum mechanical. That's the key point.
Professor Nanar, can you take over from here also?
Yeah, thank you very much, Professor Puri, for a wonderful talk. I mean, covering the phase transitions right from the basic to take into the depths and really in all without almost with zero mathematics, as you very nicely said. Also, thank you for offering to answer the questions of all our viewers on your email. Your email has been shared on the YouTube chat. And I really, really appreciate your taking time and giving this talk. Thanks to Dr. Jaiswal for conducting this talk so nicely. And thank you to all the viewers who joined through Zoom as well as on YouTube. We look forward to seeing you again next Saturday. The next lecture would be given by Dr. Srinivas Krishna Gopal on accelerators. You will see some of the applications of now the technology. We talked about superconductors and the superfluid state. So I think the using superfluid helium for the superconducting magnets is what has really culminated in getting us the high field accelerators. So we look forward to seeing you all in the next lecture. In the meantime, stay safe and see you all next week. Thank you all. Bye-bye.
Thank you so much. Thank you.